This is my lab 2 on projectile motion. The purpose of this lab is to demonstrate how you can predict the final position of an object in projectile motion. Additionally, you want to see how accurate an estimate of the final position is when compared to the predicted position. Ideally, when you compare the predicted position from the computational model to the observed position calculated using kinematic equations, they are equal. We will do 2 predicted positions for this lab where one takes air resistance into account while the other does not. The important physics fundamentals for this lab are basically anything to do with projectile motion. So we find the time that it takes for the ball to land, where time is equal to times the initial velocity y divided by gravity, and distance equals the initial velocity squared times the sine of the angle divided by gravity, or distance can also equal the initial velocity in x times time, and both of those are just solved kinematic equations. We also need drag, where it is equal to the negative b v squared v half, where b is a proportionality constant, and we need to solve for b, so the negative b equals mg divided by v squared. Air resistance affects both velocity components in x and y. Other physics fundamentals that are important: in the x direction, there is no acceleration, meaning that the initial velocity in x equals the final velocity in x. The initial velocity in x is equal to the initial velocity times the cosine of the angle. In the y direction, the acceleration due to gravity is due to gravity. The ball can reach a max height when the velocity in y is equal to 0. The initial velocity is y is equal to the initial velocity times the sine of the angle. The first step is to observe the motion of the object. So our materials that we used were a paper ball, which we said the mass was 4.5 grams, and then 2 calibration sticks, which are meter sticks. In this experiment, it was important to make sure the object was thrown in a straight line, the camera was steady, and we also threw the ball underhand so then it would make like an arc that we could see. When we analyze the object in Tracker, we can identify both our system and our surroundings. So our system was our paper ball, and then our surroundings were the people throwing the ball, the floor, and the 2 rulers. And then that's basically what it looks like in Tracker. In step 3, we make our computational model, and basically we put in our initial conditions and as our mass, our position, and our velocity, and then also our initial time, and then we step the time based off of like an average time. And then we run our computations for net force, finding the momentum, and updating your velocity and your position, and then updating your time. For one of the models, you also use drag. Drag would be 0 for the first one, but then drag we found to be negative 0.15, and then that's basically what it looks like. So here are our observed predicted position with gravity, and then gravity and drag. So basically with gravity and with drag, they're very similar, and they actually were very close to our observed. Our observed was 0.27 for the max, and then for the others, it was a little under 0.2, like 5, so it's kind of close. So possible sources of error might be that the object changed direction, maybe because of like a combating air resistance, or the object wasn't thrown in a straight line initially. Maybe there was an error with the location of the calibration stick, or with Tracker, or error like locating with the point mass. So we want to know whether our models will predict a terminal velocity. So what, like fundamentally, basically terminal velocity without air resistance will always be like greater than the terminal velocity with air resistance, and we also found that to be true. So terminal velocity without drag, basically we can estimate between these kind of 2 points that the acceleration is basically 0. So we can say that our average like velocity between those 2 points was 2.2. So that could have been our like potential terminal velocity. And then our terminal velocity with drag, the acceleration is negative, meaning that the drag has slightly exceeded gravity, and we found that the terminal velocity is 0.98, so it's actually smaller. So this basically matches up. So what happens if we threw our object straight up instead of like in an arc and projectile motion? Would it take longer, shorter, or would it be the same? So we found that the time it would take to reach the ground after being thrown straight up should take more time than the time it takes for an object in projectile motion to reach the ground, because the object being thrown straight up reaches a higher maximum because the v sub I is all in the y direction, while projectile motion splits its initial velocity into y and x components.